In this lecture, we will learn about Dijkstra's algorithm. This algorithm is used for single source shortest path. So what is single source shortest path? Let us have a graph, or for example some cities are there and there are road connected between them, okay, and all the paths have their lengths, which is shown in this figure. Now if I ask you that, okay, let's have source A and I want you to calculate the shortest path from A to all the other cities or nodes in this graph. So this is called as the single source shortest path problem, where you have to find, okay, what is the shortest path between A to C. So we can go via A to B and then B to C. I can go from A to H, H to I to C. So many paths are there. So you have to find the shortest path from the source node to all other nodes in the graph. So how is it done? In this lecture, we will use one of the most famous algorithm known as Dijkstra's algorithm, which is a greedy approach. Okay, at each moment we make a choice that is greedy, which means it's the best possible choice at that particular moment. So we will look at the algorithm, the Dijkstra's algorithm. It's in fact quite simple. So before that, some of the data structures that we will maintain for this algorithm is, one is the distance of V. Okay, it means the distance of node V from the source node S. Okay, so distance of node V from source S, and here distance of course means the shortest distance that is found till that particular iteration. Okay, so this is one of the data structures. Another one is pi of V. So pi of V is the parent node of V. That is, for me to reach from source node to some destination node, I will be using a set of nodes in between. So whichever node I take before coming to D is the parent node of that particular node. So this is denoted by parent node. Okay, so in the initialization, what we do that, okay, when I just am starting how to find the single source shortest path, so for each vertex initially Vg is the set of all vertices. For all of them I will do, I don't know yet the shortest path, so I will make them infinity, and I don't know from where I will reach that node. Okay, so that is pi v is nil. Okay, and then we initialize d of s is 0, because the distance of source node from itself is of course 0. And for this initialized single source, we see that it's O of mod v. So this is the running time of this function, which will be used as an auxiliary function for our Dijkstra's algorithm. So now next let's see the relax algorithm. So this is also used, and this is one of the most fundamental concept of the greedy algorithm, Dijkstra's algorithm. So what happens here is, let's say there is a node V, okay, and we know that, okay, and there is a source node S. Okay, so there is a source node S. I have taken some path, some set of nodes are there here, and I know a path and distance of V, I have some estimate. Okay, then what happens, there is another node U and there is some distance from S to U with some intermediate nodes. Okay, and this is T of U. So now in relaxation, what happens, let us have an edge DUV. So what happens, I have found the shortest path for DU, and now I'm trying to relax DV. So what happens is, what I do, dv has already got some value. Now I know that from S I can reach via this path to V, the first path, or I can reach via another path, that is going from S to U and then from U to V via the edge UV. Okay, so we have one distance dV, another is for this path 2 is its du plus W UV, which is the edge cost. So this is W U comma V. So if dV is greater than this, then I should update that okay, the shortest path was not the first one, but it's the second path that is going via U and then taking the edge UV. Okay, so this method is known as relaxation, and then as we are going from S to V, the first node just before V is U, so it becomes the parent of U. So this clears the concept of parent also, that for reaching from S to V, the node just before V is U, and hence it is its parent. So next is Dijkstra's algorithm itself, and it initializes the single source shortest path. So that is done first, the single source initialization, where we made all the distance of all vertices as infinity and its parent as null, and at the same time we made ds as 0. So now what happens after this, S is the set. Okay, so S is the set, and where it is a set of all nodes for which we have already found the shortest path. And then what we do initially, it is a null set, empty set, and as we go on progressing, we will put the nodes of the graph in S. Q, again it contains all the vertices in the graph. So while Q is not empty, so we do a kind of greedy algorithm. So we extract the smallest node first, we put it in S, and then how we traverse, how we progress is that for each node V that is adjacent to the U just extracted, the shortest path node U which is just extracted, so from that we try to relax all other nodes. Okay, so from U we relax all the other adjacent nodes. Okay, so this is the thing, we will apply it here on this graph. Okay, so with the initialization, what will happen, dv will become 0, and what else will happen, pi will be nil for all of them, and distance will be infinity, and parent will be nil. So this is the status of the graph after the initialization part, and this is done in O of mod V, that is the number of nodes time. Then what happens is that we have a set that is empty now of the shortest path, and we have Q as vertices of G. So we have the Q which contains all the vertices of G. So we have a Q. So let us have all the S, T, X, Z and Y. So these are the nodes in the Q. Okay, so these are the nodes in the Q. Something going wrong. So we have in this Q, and now what we do, so while the Q is not empty, so we extract the minimum from the Q. Okay, and then we try to, for each of the adjacent node, we try to relax the nodes. So what happens, initially dv is, so extract min is based on the distance, so it is 0 for source and it's infinity for all other nodes. So S will be extracted first, s comes out here as it was 0, and then from s we try to look and progress in the graph. So we have its neighbors as y and t. These are the two neighbors. So what happens, we come to, let's say, first at t. At t we see that dv is infinity, but what happens is, if we have, so d of t is infinity now, and we have d of s plus weight of s comma t as 0 plus 10. So 10 is now less than d of t, so we have dt measured as 10 and its parent as s. Next, for y also it is infinity now, but if we take the path from s to y, so it becomes 5. So y for this, it is 5 now, and s is the parent. Okay, so this is done. So now what happens, t, the value is 10, x has the value of 5, others have infinity. Okay, so extract min, again we go and we extract min. So which one, and s now has what? So the set s consists of s, the source now, then the minimum is x, so it is t, and so t is 10 and another one is y, so it is 5, so not x but it is y. So y, from there we now, because it's greedy algorithm, so what we want to proceed to the next node which has the minimum distance, so that when we explore this part du plus wuv, so du is minimum, so 5 is, so y is taken out. So now y is taken out, and from y we try to explore. So its neighbors are t, x and z. So y to t, let's try to see first for t. So for t what happens, it's already 10 now, d of t is 10. So from y if we go to t, so it will be 5 plus 3, so it will be 8. So it will be, t will be updated, it becomes now 5 plus 3 8, and its parent is now y. Okay, so you can see from s to t it was 10, but from s to y, y to t it's 8, so it's updated. We go to x, d of x is infinity. Now if we go via y, it becomes 5 plus 9, so 9 plus 5 is 14. X now becomes 14 and its parent becomes y. For z what happens, it's infinity, now it becomes 5 plus 2 7. So for z it is becoming 7 and it is y. So this is done. So we have relaxed all the nodes from node y. So it means now node y is relaxed. Okay, so from node y all the other nodes are relaxed. So let's see now. So y has come out, we have t, now it is 8, x is 14 and z is 7. So which is the minimum? Now z is the minimum, so we extract z and have it in s. So 7, so from z I can go to s, I can go to x. These are the two nodes. So if I go to s, so and s, so let's try to see this case. So while q is not empty and we extract min, and for each v adjacent to u, so we try to relax all the previous nodes also which even have come out from the q. So z, so we relax s, so s had a 0 value initially. Now if I go from z, it is 7 plus 7, so 14, so it's of no use updating s. I can go to x, the value will be z is 7 plus 6 is 13. For x it is 14, so x is updated. So z, it is 7 plus 6 13, so x gets updated, it becomes 13 and its parent becomes z. So this update happens, so x is 13 now, and for us, so z also has come out, and t was not connected here. So now we are left with t and x. So t is the smaller one, so we go to t, and what we see, so we see that from t I can go to y and x. Okay, so y, what happens from t, if I go to y, so it will be 12, and y is already 5, so it is not getting updated. From t, if I go to x, so it will be 8, t is 8 now, so 8 plus 1 9, x is presently 13, so x now becomes via t, it will becomes 8 plus 1 9, so x gets updated, so it becomes 9 with the parent as t. Okay, so this gets updated and x now becomes 9, and nothing else happens as such. Okay, so x is 9, and now the only one, so t is gone now. Now only thing left is x. So from x I can just go to z, and x has value of 9 and z has of 7. So if we go to yx also, it will not relax and make z the distance smaller. So we are done, and we see that we have z. This is the final status, and we see if distance of s is 0, distance of t is, so t is 8, and it is via y is its parent. So t I have to go via y, y's parent is s, so that distance is s to y, y to t. Then for x we are going via t, so s to y, y to t, t to x. Z is via y, so s to y, y to z, and y is via s. So this is the idea, okay, for the Dijkstra's algorithm. So now let's try to analyze the runtime. Okay, so this is, as we saw, initialize, solve vertices, it is O of mod v. Okay, then we have S is null set. Q, let us have a queue that is just simple array of size mod v, of size of nodes, while q is not empty. So this while loop runs will all, and in each while loop we extract one of the nodes. So this will run mod v times. U is extract min. So if you have an array of q is an array of size v or mod v, so if you have to extract the minimum, so it will be cost of O mod v. Okay, so this is mod v times. So this will run for each time, so it will be O of mod v square. S is S union U, so added. For each vertex v adjacent to U, relax UVW. Okay, so let's see the relax. So relax is just a constant time algorithm of function. Then what happens, let's try to see in this one how much is this part going to run. So for each of the nodes this is running, and this part, what happens for each vertices v adjacent to U. So for each of the nodes, so if we have like this in a graph, so for each adjacent nodes it is working and relaxing. So it means all the degree of that particular node I'm traveling, and this is happening for all the nodes. So if you try to understand this in a simple graph, so if I am at this node 1 2 3, at node 1 I cover 3 and 2, so d of 1 is 2, Then again at 2, if I'm trying to relax for all nodes, so D2 is also 2, and D3 is again I try to relax all other nodes, so it is 2. So total D1 plus D2 plus D3 is 6, and it's basically twice the number of edges. Okay, so this whole thing I'm going for all the vertices I'm doing, and for all of them I am looking at their edges. So this is happening twice the edge number of times. Okay, so this is happening these many times. So this is O of mod V square, and this is happening for mod V mod E. Okay, so something like that. So this is in fact happening for just mod E, because mod twice E. Okay, and one more relation, if you see that number of edges, if we have mod V vertices, so we can, if we even connect each vertices to all other vertices, so we have mod V choose to these many edges, which is equal to mod VO of mod V square. Okay, and so mod E is less than equal to mod V square, hence this is also, so this is equal to O of mod V square plus mod V square is equal to O of mod V square. Okay, so we see that this Dijkstra's algorithm takes O of mod V square if we have a Q that is an array. Okay, and if you have something different for the extract min, then your algorithm complexity will be different. So this was a lecture that gave you basic idea about the Dijkstra's algorithm and its analysis. So I hope you like this video. If you like this, please subscribe to my YouTube channel.